So now we're going to talk about the remaining two plate tectonic boundaries. We already, in the previous segment, have dealt with the divergent plate boundaries, and now we're looking at convergent and transform faults. So convergent is where two plates are coming together, and here in this case we have a continental plate. That means the lithosphere of the mantle is capped with a piece of continent, and here we have an oceanic plate. So this is the newly formed basalt. This is divergent. Remember, two arrows are going away from one another, and here is a convergent plate boundary. These two pieces of lithosphere are approaching one another, and the landform that is characteristic for that is a deep ocean trench, and it's just above what we call the subduction zone. The oceanic crust is much denser than the continental crust, and so it will have to go down and it will dive below the continental crust, and this is what we call subduction zone, and there is a little bit of drag, and that forms a deep trench. Now these trenches are really deep. They are 11 kilometers deep, and if you consider that the highest mountain on the continent, Mount Everest, is 9 kilometers high, so the trenches are even going deeper than the highest mountain. Here's an animation. It's a little bit pixelated, but you see the oceanic plate going down. That's over here, typically shown as a dark basalt. Here's the continent, and that would be at the west coast of North America.
The plate on the left is capped by dense oceanic crust formed at a spreading ridge. When it encounters the plate on the right, with its thicker and less dense continental rocks, it subducts.
It comes under high pressure.
The blue dots represent water that was incorporated by hydrothermal circulation of seawater near the spreading ridge. Subduction carries this water into the mantle, where it is released, triggering melting of the overlying mantle rocks. These water-rich melts are less dense than the surrounding rocks and buoyantly rise, accumulating in magma reservoirs in the continental crust. Some of these magmas eventually erupt and build subduction zone volcanoes.
Below the continental plate, we find not just one volcano, but chains of volcanoes that are erupting. And they're neatly lined up parallel to the edge of the continental plate. And if we step back a little, then you see this whole chain of volcanoes outlining a large portion of the west coast of North America and going into Canada and the Aleutians. So California has a few of those volcanoes. There is, for example, Mount Shasta. Then the Cascade Range is also pockmarked with volcanoes and continues in Washington State and goes further into Canada. So in this way, because of the melt that is occurring underneath, below the overriding plate, in many cases a continental plate, we have a ring of volcanoes, and we call this a Pacific Ring of Fire, and it forms the volcanoes in the Andes, in the Philippines, in Alaska, and they are all an indication of subduction zones. Here is a picture of the Ring of Fire. Some people call it the Circum-Pacific Volcanic Zone, but Ring of Fire is sort of easier to understand. In the middle of the Pacific Plate, we have different volcanoes. So we'll talk about those in a little bit. So this is how you can build mountains. You have an ocean-continent plate convergence, and there is some deformation going on at the fringes. The same with ocean-ocean plate convergence, but the really big mountains are forming due to continent-continent plate collision, not just convergence, but collision, because you don't have a subduction zone involved. Continental plates are relatively light, and they do not usually get subducted into the mantle, so they are colliding on top of the mantle and form huge mountain ranges. Here we have Pangaea disassembling again and forming the configuration of continents that we know. And again, watch India jamming into the Eurasian plate and forming the Himalayas. See, it has an enormous impact. And if we get a little closer to the Himalayas, again, I know this is a bit pixelated, but it's still a nice animation. So we see the Indian continent approaching the Eurasian plate, closing the ocean in between them, pushing some of the continental shelf sediments up on top of the mountains and forming this huge mountain system called the Himalayas, which is still rising since India is still pushing. And this process then finally explains why we find shells on top of the highest mountains, because they are the remnants of the former continental shelf that could not be subducted but has been pushed up on top of the mountains. Amazing. Okay, we're left with one with one type of plate boundary. That's a transform fault, when two plates are trying to make room for one another. And when you look at an image of the seafloor, you can see these lines here that look suspicious. Here, of course, we have the mid-ocean Atlantic ridge. Here we have the East Pacific rise, and then we have these long fracture zones and transform faults. So let's see what's happening. Remember, the planet is spherical or almost spherical, and you're pushing plates apart or towards one another over a curved surface, and the plates are moving in different directions. They're moving with different speeds. So these transform faults here are helping to negotiate all these different movements. Here's, you may remember this. This is a mid-oceanic or an oceanic ridge. You see the arrows indicating the spreading directions. And right here, where two arrows on two different plates are going in opposite direction, this is what you call a transform fault. So the transform fault is basically connecting the pieces of the divergent spreading. Here, you see two arrows going in the same direction, same over here. So these are not transform faults because they are only forming fracture zones. Transform faults are between the segments of the ocean ridge that are being displaced. Let's watch that again. So these are the transform faults, and these are fracture zones, transform faults over here. And most likely the most notorious transform fault is the San Andreas fault, and you can see here how it has displaced these two blocks, Miocene and Age. That's why they have an M here. And now we find them on opposite side of the fault. The arrows are indicating the direction, the sense of motion of the fault. We call it right lateral fault, because if you stand here, you look across the fault and you see that the rocks or anything that used to be connected has now moved to the right. Like, look again at the Miocene block. It has moved from your perspective here, when you look over the fault, to your right. And the same is true if you're standing here and you look across the fault, it would also have moved to your right. So the San Andreas is a right lateral transform fault. So this is one of the transform faults that is on land, but it used to be a portion of the ocean floor and was connected to a divergent spreading center. And here's the story, very, very interesting. Look at this. This is 38 million years ago, and this is a symbol for subduction zone, these kind of teeth. And you see the motion of the oceanic plate. They're separated by a spreading center. This is the East Pacific rise. And let's see what happens. So until 25 million years ago, this was mainly a subduction margin. But now, the transform fault is docking on the North American continent, jumping online, and is grabbing a few pieces, and it's breaking them off the North American plate. Let's do this again. So you see this transform fault here, making landfall, basically, jumping on land, and the Pacific plate keeps on pushing. It's extending the whole area, and this little block here has to move now as part of the Pacific plate north. Any idea where this is? I'll let you watch it one more time. Subduction zone, the end of subduction in this portion. This San Andreas is moving on land, and it's getting longer and longer. It has to move with the Pacific plate, breaking off this block here, which becomes our transverse ranges. Wow. Tanya Atwater, of course, made also this animation. And in a close-up during the last 20 million years, you can see that again. SD San Diego, SB Santa Barbara, SF San Francisco. So you see where we were. The rocks, many of the rocks that are now in our hinterland, that is part of our mountains, actually came from further south, from San Diego. So the Pacific plate is extending in this direction and allows extension. Big basins are opening here. The Santa Barbara block wants to go with it, but it's being pressed against the North American plate. And now, a few million years ago, these rocks then become mountains. So the mountain system, the Santa Ynez Mountains behind us, are all relatively young. But that explains why we have an east-west oriented coastline and why we have mountains here. Whereas the rest of the coastline is going more like this, north, northwest, south, southeast, but we have this kind of east-west coastline with the South Beach, and we are actually part of the Pacific plate. You see this, the new plate boundary here is now the San Andreas, which has gotten longer and continues to get longer. Now it's about 1,300 kilometers long. And it's creating trouble. We have a big bend here, and the rocks here are being pushed out towards the ocean. They're getting thinner in this direction. They're getting longer in that direction. Let's watch that again. And this nice oval is getting squeezed and folded and faulted. That's a very interesting situation. And actually, California has it all. It has divergence over here. Here's some spreading. It has the transform fault along most of its length, and it has a little bit of subduction still going on in Northern California. Wow. So if you look at maps with plate boundaries, you usually have a double line that is indicating divergence. Also, those arrows are indicating where the plates are going. Convergence, these teeth, and the teeth are pointing in the direction of the overriding plate, which is usually a continental plate. And then where plates are sliding past one another, transform faults, you see those arrows going in opposite direction but parallel to the plate boundary. Now, what is the mechanism of plate motion? Probably all three of them, but right now slab pull, basically gravity pulling on a plate when it goes down into a subduction zone, helps to open up a divergent spreading center at the other end. Possibly there is some pushing from the ridge, that means from the central valley of the divergent spreading center, involved as well, and convection currents in the mantle. But to which degree these other mechanisms are involved, we are not quite sure. Now, here's something else. Another phenomenon related to plate motion, but these are hotspot volcanoes, and you find them anywhere. It could be at the margin of a plate, in the middle of the plate. There is one interesting hotspot, that's Iceland, that is sitting also on top of a divergent spreading center. But many of the other hotspots are found on oceanic plates, and so here's a story. You have a mantle plume that is relatively stationary and sends out streams of hot magma to the surface, and they're puncturing the lithosphere and forming a volcano. Now, the plates are not standing still, and then they are moving away from the source of the mantle plume, which is then called the hotspot, and then the hotspot is breaching through at another location and forming another younger volcano. And the best example we have are the Hawaiian Islands, where you have a string of volcanoes, and they're getting younger and younger towards the most recent and active volcanoes in Hawaii. Actually, we have another one that is to the southeast, and it's trying to break through and and make another resort, but it will probably be several tens of thousands of years until it comes to the surface. So I give you a minute to think about how fast plates move. Do you know? Don't have a clue? What plates? That's of course not a good answer. Well, some people say plates move as fast as fingernails grow. 1 to 20 centimeters, 10 to 200 millimeters a year, so maybe up to 8 inches. That would be fairly fast. That doesn't sound like much, does it? Well, look at this one here. That's 37 years of fingernail growth, and I don't know how long it took this lady to have these beautiful fingernails until she had those established. Both of them are in the Guinness Book of Records, and well, it's kind of weird. But my point here is, if you take this 37 years, stretch it out, take it times 5, and take it times 1,000,000, then you have the opening of the Atlantic Ocean. So it comes together given enough time, and geology has anything but time. You may remember that we talked about the rock cycle, where sedimentary rocks may be buried, that they become metamorphic rocks so hot and pressurized that they melt. Magma develops that forms plutons or volcanic rocks, and when the volcanic rocks are back at the surface, they may disintegrate to form sediments. Well, we can also look at the rock cycle in light of the tectonic cycles and plate tectonics. For example, we have some sediments that are being collected in the ocean. They accumulate, let's say, above a subduction zone, and then are being lithified, possibly getting subducted again, melting back up, becoming part of the magma, the lava, and disintegrating to become sediments again. So the tectonic cycle, the plate tectonic cycle, is an important portion of the rock cycle and bringing new rocks to the surface. Actually, without plate tectonics, you wouldn't have any new mountains. Weathering would wear them down, and the surface would eventually look like Australia or portions of South Africa, flat and featureless, without any activity, without earthquakes, without volcanoes, and without downhill skiing.